Hey everyone, welcome to yet another video in FAA using SolidWorks. So in this video, we'll discuss about what a static analysis is and how it's different from a dynamic analysis and what are the other different types of analysis that is available in SolidWorks and when do we use them. Let's begin with the PPT. So structural analysis. So the term structure not only refers to the civil structures like bridges and buildings, but it also can be used to refer the mechanical parts that we often use in an industry. To understand the stress and strain produced by the loading on these mechanical structures, we perform finite element analysis to understand the behavior. Here in a finite element analysis, the unknown displacements are initially found out and then they are resubstituted back to get the reaction force and other derived quantities like stress and strain. Basically, a structural analysis problem can be classified into static analysis and dynamic analysis depending upon the loads that are acted upon. Apart from this classification, we do have 1D, 2D, 3D finite element analysis that is classified based upon the element that is used. We have several other specific analysis like the buckling analysis, fatigue analysis, which serve the purpose that they were designed for. So SolidWorks has separate modules for each of the special analysis. Now let's look at the basic classification of analysis, that is static and dynamic analysis. If you consider a static analysis, we assume the forces that act upon the model are quasi-static. In other words, the loads that are acted upon on the model increase gradually such a way that the acceleration, velocity, they can be neglected. While on the other hand, the dynamic analysis, all the inertial and damping effects are considered and we solve for the acceleration and velocity of the components before we find out the stress and strain. So compared to a static analysis, a dynamic analysis is much more time consuming. So also if you consider in a static analysis, you start the simulation at point A and if B is your final end, the intermediate results that you get may follow any path and get to the final results. Hence, you can never rely upon the intermediate values in a static analysis. On the other hand, in a dynamic analysis, if you have two destinations, the path will be precise that the intermediate values that you get for stress and strain are reliable and can be used. To be even more specific, let's consider bending of a cantilever beam and I fix it in this side. I'm going to bend this by applying a force. If we perform a static analysis, as the stress value increases throughout the simulation, we get a final stress contour. This final stress contour can be relied upon, while the intermediate results produced by the pseudo time stepping of the solver cannot be relied upon. This is not the case with the dynamic analysis. Here if you apply the same load on the cantilever beam and perform a dynamic analysis, you can see how gradually the stress increases and at each time step at 1 second, 2 seconds, that is if you want to look at the stress result at the end of 5 seconds, the results prior to the final step, that is the first second results, will be reliable as well. Hence the dynamic analysis requires more computational effort than a static analysis. So depending upon our requirement, we tend to choose either we want to perform a static analysis or a dynamic analysis. And finally, to put it short, if someone is interested in looking at the deformation at the end of loading, so they can just perform a static analysis, look at the final deformation. If you are interested in looking at how the deformation progresses, you can perform a dynamic analysis on it. Now let's get back to the slides. As discussed earlier, any material will have an elastic region beyond which it is going to behave non-linearly and finally end up in the failure zone. Hence, to capture all these non-linearities, we do have specific types of analysis that is classified as linear and non-linear. In order to capture the non-linearities in a static or a dynamic analysis, we have specific analysis types to differentiate between these loads. So to understand it in a better way, let's open SolidWorks. Click on File, open a new part. Make sure the unit systems are as per your requirement. Now click on the front plane, right click and edit sketch. Draw a rectangle using the corner to corner method. Use the smart dimension to input 50 mm and a 50 mm for both the length and the breadth. Click OK. Now select this circle, place it exactly in the center point of both the sides. Dimension it as 10 mm and click OK. Now in order to constrain this circle into the center of the circle, click on this dimension, select this side and choose this point here and input a value of 25 mm. Similarly, choose this side and select the center, input a value of 25 mm. Now that we have fully constrained this geometry, click on the features here and select the extrude option. Input a value of 5 mm and click OK. So now we are going to perform a static analysis on this part and understand when we need to perform a nonlinear analysis on such a simulation. So this finite element analysis on a plate with a hole is a basic problem that any FEA engineer would start with while learning a software. So let's proceed with the simulation. Click on simulation, choose a new study. Let's perform a static and click OK. Now for the material, let's select alloy steel, which is the default material. So the yield strength is about 620 megapascal. Click apply and close. Now that we have defined the materials properly, right click on the fixtures, select the fixed geometry and choose this face. Make sure you choose the face and not the edge here. Click OK. Let's apply a load on the other face. Select the face. You can see if you apply the load now, it's going to be a compressive type of force. We are interested in applying a tension force. So input a value of 1000 Newton and reverse the direction. Click OK. So let's use the default mesh for the demo purpose. So click on OK. So this is our meshed model. This looks fine. Let's proceed with the simulation and run it. Okay, now that our simulation is done, let's look at the results here. You can see the yield strength is about 6.2 into e power 8 and the stress values are well below this yield strength value. So this stress result is acceptable since there is a linear relation between the stress and the strain within the elastic limit. If you increase the force by a factor of 10, your maximum 1 measure stress should also increase by a factor of 10. So right click and run the simulation. So as you noticed that there was a similar change. So now let me increase the force value by a factor of 10 and rerun the simulation. So you can see in the legend, so we have a arrow pointing to the yield strength value. Thus, any value that is being plotted above this yield strength value is unacceptable. That is, we have to perform a nonlinear analysis to get realistic values from this simulation. Hence, in any case, if you are performing a static analysis and your stress values are above the yield strength value, you should not use those values. You need to switch over to a nonlinear analysis to get reliable results. Let's copy the same simulation and perform a nonlinear static analysis. Click OK and run this analysis. You can notice that the solver is taking much longer time than it took to solve a static analysis. And here you can see the strain values are not as high as the static analysis. That's because if you consider the stress strain graph, if the relation between the stress and strain is linear, you can see the displacement gets larger as the stress value increases. And when it enters a nonlinear region, as the displacement increases, the stress value doesn't increase that much. Hence, in the static analysis, our solver followed this extrapolated path such that for any value of load that we give, it received the corresponding stress and strain by just extrapolating this curve.